Log on, tune in, find out. Another good idea from Cambridge.
My pleasure to welcome Ben Martin from Canterbury, who will tell us about complete reducibility and rationality. And then, as usual, we'll meet at 5:30 to go out for a drink afterwards.
Okay, well, thanks very much. I'd like to thank the organisers of the program for organising it and for giving me the chance to come along and also giving me the chance to speak. So I'm going to talk about complete reducibility and rationality. I see I've actually written separability on my piece of paper here. I'm still a bit jet lagged, I'm afraid. So the first thing I should say is that everything I'm going to talk about is joint work with Michael Bate, Gerhard Röhrler, and some of it also with Rudolf Tanger. So complete reducibility is a generalization of an idea from representation theory of a completely reducible representation. It's an extension of that to cover arbitrary reductive algebraic groups, and the usual representation theory is the case of general linear groups. And this has turned out to be quite useful in understanding some problems involving reductive groups, subgroup structure of reductive groups, finite groups of Lie type. Most of what's been done up to now has been working with reductive groups defined over an algebraically closed field. And the second part of the talk will be about the case where the ground field is not algebraically closed, where there are some interesting problems that come up. So the first part of the talk will be an introduction to complete reducibility, and then the second part on rationality will be about these problems over non-algebraically closed fields. So let's start with complete reducibility. So we're working with algebraic groups over a field K. And I'm going to assume in the first part of the talk that K is algebraically closed. And K will have characteristic P. And I'm going to assume that the characteristic is greater than 0. Pretty much everything I say makes sense in characteristic 0. It's just a lot less interesting. Characteristic P is the interesting case. And so I said this a moment ago, but I'll write it down. Assume that K is algebraically closed for now. So this bar denoting algebraic closure. And we're going to be looking at connected reductive algebraic groups. So I have this word connected in here. Many people take connected to be part of the definition of what they mean by a reductive group. We tend not to, but I'm going to stick to connected groups in this talk. But it's worth pointing out that most of what I'm talking about also makes sense for non-connected reductive groups, and there are some interesting problems there. But just to keep things simple, I'll stay with the connected case. So many of you in this room will be very familiar with reductive algebraic groups. Maybe there are one or two who are not so familiar with this sort of stuff. So perhaps I'll just quickly recall a couple of examples. So the general linear group, the special linear group. What else do we have? Special orthogonal groups, symplectic groups. The multiplicative group of the field. These are all reductive groups, and more generally, you can make more complicated ones by sticking these together. You can form products. And the point is that these are all classified. These are all there's a list of these things. So now we come to the definition of complete reducibility, and this is due to Serre back in 1997, I think, or possibly 1998, I don't remember. And so suppose we take a subgroup H of G. When I say subgroup, I'll always mean a closed subgroup. Then we say that H is G completely reducible, and I'll just abbreviate that as GCR. If whenever we have a parabolic subgroup of G that contains H, so these are the extremes. What about the stuff in the middle? So what about reductive groups that are not linearly reductive? If H is reductive but not linearly reductive, well, it might be G completely reducible, or it might not be G completely reducible, right? It all depends on the way in which H is sitting inside G. So this, so the notion of complete reducibility, it doesn't just depend on the groups H and G in themselves, it depends on the way that the small group is sitting inside the big group. Another example. So I said that I'm going to assume in this talk that the characteristic of the field is positive always. Well, I'll just break that rule for a moment and point out that if the characteristic is 0, then a subgroup H is G completely reducible if and only if H is reductive. So in characteristic 0, it kind of doesn't depend on how H is sitting inside G. It just depends on what H looks like itself. So this is why I said before that in characteristic 0, this notion is not so interesting. So now I want to spend a couple of minutes to try to convince you that complete reducibility is an interesting and useful property to be looking at. So we have this dichotomy. If you have a subgroup of G, either it's completely reducible or it isn't. Well, that's pretty trite, but the point is that this is a useful distinction to make, because in both cases there are interesting things that you can say. And so if you're doing something like, so suppose you're interested in the subgroup structure of reductive groups. Suppose you're interested in the question, how can one reductive group sit inside another reductive group? Then it can help you when you're looking at subgroups of a reductive group to ask the question, is this subgroup G completely reducible? If it is, then you do one thing, and if it's not, then you do another. So either H is GCR or H is not GCR. And there are interesting things to be said. So I'm going to give an example in a minute where you do see this kind of dichotomy at work. So what kind of interesting things can you say? Time for a theorem. Theorem 1, BMR. So B is for Bate, M is for Martin, and R is for Röhrle. If a subgroup H is GCR, then its centralizer in G, in the ambient group G, is also GCR. Right? So if you're trying to understand subgroups of G, if you know that your subgroup is completely reducible, then its centralizer is also completely reducible. So that tells you something about what the subgroup H must look like. Another result, just M this time, M for Martin. Suppose we have a finite group F, and we look at ways of embedding F inside our ambient group G. So let's look at homomorphisms from F to G. There exist only finitely many homomorphisms, finitely many conjugacy classes of homomorphisms from F into G whose image is completely reducible. G completely reducible, so just GCR. So if you remove this restriction on the image, then this is just not true, right? It's not true that there are only finitely many conjugacy classes of embeddings of a finite group to a reductive group G. There are very simple counterexamples. So this G complete reducibility condition is quite nice because it forces this kind of finiteness that you get here. So these are nice things that happen if you're talking about completely reducible subgroups. Well, what happens if you're talking about a subgroup that's not completely reducible? Theorem 3. And I'm going to be coming back to this, or to this idea again and again and again. You'll probably get sick of it by the time I finish the talk, but it turns out to be very important. So suppose suppose our subgroup H is not G, completely reducible. Then, well, by definition, this tells us that there is a parabolic subgroup that contains H, and such that no Levy subgroup of the parabolic contains H. What this theorem says is that there's actually a best parabolic subgroup that does this. There's a kind of a canonical one or an optimal one. And this has some nice properties. So there exists an optimal, I'll put these words in quotation marks and then explain what they mean in a moment, destabilizing parabolic subgroup. Let's call it P sub opt of G, such that P sub opt contains H, now what about these words in quotation marks? Destabilizing means that no Levy subgroup of this parabolic contains H. So this means no Levy subgroup contains H. And it's worth noting here that in particular, this implies that P is not equal to G. Okay, G itself is a parabolic subgroup, and G is reductive. So G is a Levy subgroup of itself. So obviously, if you're in this situation, the parabolic can't be equal to G. It's a proper parabolic subgroup. Now, what about this word optimality? Optimal. I'm going to fudge things a little bit here. So this means, well, for the purposes of this talk, that P opt is stabilized by any automorphism of G that stabilizes H. And I'm going to be deliberately vague here by what I mean by automorphism. I don't just necessarily mean automorphism of algebraic groups. I'm also possibly allowing things like field automorphisms or Frobenius or stuff like that. Well, in particular, this covers inner automorphisms. So what does this mean? In particular, the centralizer of H is contained in P opt. Okay, so the centralizer of H acts on G by conjugation, and of course it stabilizes H. It just commutes with H. It doesn't do anything to H. Therefore, it must stabilize this optimal parabolic. By stabilize here, I mean normalize. But parabolic subgroups of a connected reductive group are self-normalizing. That's a standard result. So that tells us that the subgroup CG of H that normalizes this parabolic must actually lie inside it. So this is a very nice thing. You have this parabolic that not only contains the H you started with, but it also contains the centralizer of H. And in fact, if we go back to theorem, still on the board here, theorem 1, you can prove theorem 1 by using this optimality result, theorem 3. I don't have time to say anything at all really about proof. other than that it involves geometric invariant theory. So there's quite a geometric formulation of what it means for a subgroup to be G completely reducible. And in this setting, you have tools from geometric invariant theory that you can use. And one of these is the so-called Hilbert-Mumford theorem, which I'm sure many of you will be aware of. And then there's the strengthening of it due to Kempf. And the optimality here, why do I use the word optimal? It suggests best, it suggests optimizing some function. And if you do this construction, then you are actually optimizing some real valued function of something in order to find that parabolic. But I don't have time to go into that now. Oh, I should also mention here that this involves work of Roger Richardson. So those of you who work in geometric invariant theory or have come across it before, you may have come across notions like stable points, unstable points, semi-stable points, stable or semi-stable vector bundles. And the use of this word destabilizing here is that comes from geometric invariant theory, so it's consistent with the way that the word is used in geometric invariant theory. The idea is that you have your group G is acting on a variety, and you have a point, and you're kind of moving that point outside its orbit somehow. Right. So let's stick some of these ideas together and look at an application to finite groups of Lie type, LMS 2005. So the M is me again, the L is Martin Liebeck, and the S is Anar Shalev. So we wrote a paper on understanding maximal subgroups of finite simple groups, trying to obtain bounds on how many they are. Well, really, I should say that they wrote the paper, they wrote all this stuff, and then my contribution was some results involving some of the stuff about complete reducibility. So suppose we have a Frobenius map. So this is a homomorphism of algebraic groups from G to itself, whose fixed point set is finite. So suppose we take a subgroup F of G sub sigma. So G sub sigma means the fixed points of sigma. So this is a finite group, so F is a finite group. And so this particular result that I'm going to write down, this is a dichotomy. F is G completely reducible, or there exists a proper parabolic subgroup which is stable under sigma. A proper sigma stable parabolic subgroup P of G such that F is contained in P. So why is this useful? You want to understand conjugacy classes of finite subgroups of G sigma. So suppose you're in the first case, F is G completely reducible, then you can look at this result over here, theorem 2, and this tells you that there are only finitely many conjugacy classes of homomorphisms from F into G whose image is completely reducible. And kind of the issue here is that if you have a fixed G, you have a whole infinite family of these Frobenius maps. Just the standard Frobenius where you raise, think of G as being SLN, and think of the map that just raises matrix entries to the Q, where Q is a higher and higher power of the characteristic P. You get a whole bunch of these Frobenius maps, and the sort of thing that you may lose control of is when you're talking about conjugacy classes, is what happens when you go from one of these Frobeniuses to another. And this result here is over the algebraic closure. So this kind of gives you some control over what happens when you consider these infinitely many possible Frobenius maps. So in case 1, you get some control. In case 2, it tells you that you're in a proper parabolic subgroup of G. And then you can do things like pushing down into a Levy subgroup of P, and you then have a smaller reductive group to work with. And then you can use some kind of induction argument. Actually, there's a hypothesis here that I left out. So let's put this back in just to be on the safe side. Yeah. So for arbitrary reductive groups, this is more complicated. Gerhard's PhD student Daniel Gold has been looking at this and trying to investigating whether this result extends to arbitrary reductive G. Someone once told me that every good talk should have a proof. This talk has 3 proofs, but actually it's the same proof repeated 3 times. So here's the first. Here's the first go. Well, if f is G completely reducible, then we're happy. So suppose it's not. Well, then we look at our theorem 3, which is still on the board over there. And theorem 3 gives us this optimal parabolic subgroup. So let P, the parabolic subgroup that we're looking for, be equal to P opt. And then, just by definition of this optimal parabolic subgroup, it certainly contains our F. The issue here, though, is we need to know that this is sigma stable, right? Now, how do we know that? Oh, and notice also that this is proper. This is the remark that I made once at the end of the discussion of that theorem. Well, sigma is an automorphism of G, or at least an automorphism of abstract groups, not necessarily an automorphism. Well, usually not an automorphism of algebraic groups. Since sigma stabilizes F, because F is a subgroup of G sigma, which is by definition the sigma stable point, so sigma certainly stabilizes F. So since this is the case, sigma stabilizes P. Why is that? That's just by optimality. There are some slightly unpleasant details buried here. This stuff about stability under automorphisms, it all works very nicely if you're looking at automorphisms of algebraic groups. If you're looking at things like field automorphisms or Frobenius automorphisms, because they're automorphisms of abstract groups, but not automorphisms of algebraic groups, it's a wee bit tricky, and you have to be a bit more careful. But anyway, this follows essentially from theorem 3. So that's the end of the proof. This is what you wanted. This gives you your sigma stable proper parabolic subgroup that contains F. So that's the end of the first part of the talk. Perhaps I'll leave theorem 3 on the board, because we're going to need it again. Now the second part, rationality. So by this, I just mean we're going to consider algebraic groups that are defined over a not necessarily algebraically closed field. Just repeat the definitions and see where it takes us. So now we're going to allow K to be different from the algebraic closure. And now we're going to assume that, well, again, that G is a reductive algebraic group defined over K, and H is not just any old subgroup, but a K subgroup. So a subgroup that's also defined over K. So if you're not familiar with this sort of stuff, then just very roughly, the complex numbers is an algebraically closed field, so you have the group GL and C. The real numbers is a subfield of the complex numbers GL and R. You can think of as a reductive algebraic group defined over the real numbers. So very roughly speaking, when you're asking whether a subgroup is a K subgroup or not, you're asking is it a matrix subgroup whose entries lie in this subfield K. That's very roughly. So now the definition. So when Sear gave his definition, he gave it over an arbitrary field. He didn't sort of split up into the algebraically closed case and the non-algebraically closed case as I've done in this talk. So H, our subgroup H is G completely reducible over K. It's a bit of a mouthful, so we'll abbreviate that. If, well, the same as before, but instead of looking at all parabolic subgroups and all Levy subgroups, we just look at parabolic subgroups that are defined over K and Levy subgroups of those parabolics that are defined over K. And where it gets tricky is that you may have a parabolic subgroup that's defined over K. Some of the Levy subgroups of that parabolic will be defined over K, but there'll also be a lot of Levy subgroups that are not defined over K, and this causes problems. So to finish the definition, if whenever E is a K parabolic subgroup of G that contains H, there is a K-defined Levy subgroup L of P that contains H. So let me remind you just once again, if you're not familiar with this, that the Levy subgroup of a parabolic subgroup, it's not unique. It's unique up to conjugacy, right? But unique up to conjugacy still means that there are lots and lots and lots of them. And as I said before, some will be defined over K and some won't. And so in terms of the original definition, G completely reducible without any mention of the field, that is just the same as G completely reducible over the algebraic closure. And so there's a really obvious question to ask. How are these notions related to each other? So if your subgroup, you have a subgroup H defined over K. If it's G completely reducible over K, does it have to be G completely reducible? Conversely, if it's G completely reducible, does it have to be G completely reducible over K? Right. And the answer to that is no. So in the forward direction, McNinch found an example of, or a construction of a subgroup which is G completely reducible over K, but not G completely reducible. And the construction is not so hard, and it's in some sense generic. So what I mean by that is that it works for every characteristic P. What about the other direction? Well, for a while we thought, or perhaps I thought, not so sure about the others, that the implication was true in the reverse direction. And then a couple of years ago, we found a counterexample. So this is the paper was accepted last year, but it hasn't appeared yet. And so this example where you have an H contained in, it's sitting in the exceptional group of type G2, and it's actually sitting inside an A1 subgroup. So sitting inside a product of commuting SL2s inside G2. This H, well, as a group, it's very simple. It's just the symmetric group S3. And now the important thing, the characteristic is 2. So this is something that only works in low characteristic. So we think we haven't actually proved this, but we think that this can only happen in low characteristic. And it should be pretty hard to find counterexamples like this. So if you wanted to formulate that more precisely, if the characteristic is good for G in the usual sense, then this sort of thing probably can't happen. What about some positive results? What are some conditions on H and G in the field that will make this true? So here's a condition. So suppose our field is perfect. Then the answer to the question is yes. H is G completely reducible over K, if and only if H is G completely reducible. So we proved it in both directions, but I'm just going to show you the proof in one direction because it fits in with the theme of the talk, and it's the same proof as I showed you before. I believe in recycling. So it's this direction. So suppose H is not GCR. Suppose H is not G completely reducible. So what do we want to do? We want to find a parabolic subgroup that contains H. And the parabolic should be defined over K, and no Levy subgroup of that parabolic defined over K should contain H. So what do we do? Well, just as before, we take our parabolic subgroup to be this optimal guy. Okay? So our group G is defined over this field K, which need not be algebraically closed, but just forgetting about the smaller field for a moment, it's also defined over the algebraic closure, and so theorem 3 that I was talking about before still holds. So let P equal P opt. Then H is the subgroup of P, just by definition of the optimal parabolic. Now we want to show that this optimal parabolic is defined over K. How do we do that? Well, maybe you can guess already from what we were talking about before with the Frobenius maps. So since the Galois group stabilizes H, it also stabilizes P. Why? It's by optimality again. And this tells us that P is defined over K. And here's where we use the fact that K is perfect. Okay, this is the Galois criterion for rationality. And now we know that H is not contained in any Levy subgroup. Of P. Okay, that was part of theorem 3. So in particular, it's not contained in any Levy subgroup that's defined over K. So we actually have something that's a bit stronger than what we want here. But we're not going to complain about that. So this tells us that H is not G completely reducible over K. So the proof in the other direction, as I said, it's a bit less interesting, so I'll skip it. Well, what's the problem for arbitrary fields? What goes wrong? Well, the basic problem, and the problem with this Galois criterion for rationality, the reason it doesn't work for arbitrary fields, is that if the algebraic closure is not a separable extension of the field that you're working with, then the action of the Galois group, it doesn't kind of pick up everything. It doesn't tell you everything you need to know. So if you look at the fixed points, or the subfield of fixed points, of the Galois group, it's too large. So it strictly contains K. So you end up getting the inseparable closure of K rather than K, which is what you want. So the sorts of problems that come up here are to do with inseparable field extensions. So separable field extensions are nice, inseparable field extensions are nasty. So in particular, if you're working in characteristic 0, then, well, the whole sort of theory is much less interesting in characteristic 0, but in characteristic 0, any extension of fields is separable, so you don't see this kind of problem. So Sarah asked us the following question. Suppose we have our field K, and suppose we have a finite Galois extension. So is it true that a subgroup H, defined over the small field K, that it will be completely reducible over K if and only if it's completely reducible over K prime? So if a group and a subgroup are defined over a small field, then they're certainly defined over the larger field. So this question makes sense. If stuff's defined over K, then it's defined over K prime. Well, first instinct is to think, aha, Galois extension, these are always separable, so this should be good, right? I just told you that separable extensions are good. The problem is, so this, well, we think this is hard. Well, this just means that we haven't managed to solve it, although we've got one direction. Why is this hard? It's hard because what you'd like to do is to relate G complete reducibility over K to G complete reducibility over the algebraic closure. So you want to hop backwards and forwards between K and the algebraic closure, between K prime and the algebraic closure, and you can't do that because there's some inseparability. So this is hard because these extensions need not be separable. So, as I said, we've got one direction, but it's kind of the uninteresting direction from the point of view of this talk. BMRT, T is for tanga, Rudolf Tanga. Which direction is it? Is this one? Oh, just by kind of a bit of messing around, really. Nothing too profound there. What about the other direction? So what I want to do to finish this talk is to point out that this optimality result over here is very nice, but it works over the algebraic closure. It uses geometric invariant theory. What we want is an analogue of this result over the field K. And it's more complicated because the geometric invariant theory stuff doesn't work so well there. So I'm going to finish by pointing out that if we have an analogue to this, then it will settle this question in the other direction. So this is the question, is there an analogue? So suppose H is not GCR over K. Does there exist an optimal parabolic subgroup, K parabolic subgroup, P opt, maybe I should call it, no, I'll just stick with P opt, G, such that P opt contains H. So if you're really concentrating hard, you may have noticed that I left out the word destabilizing because that's kind of comes from the geometric invariant theory, so maybe it's not so appropriate to use here. But what I really want is that no Levy subgroup of this parabolic, no K Levy subgroup of this parabolic should contain H. So can we do this? We know by definition of not being G completely reducible over K that there's certainly some K parabolic subgroup that contains H, and such that no K Levy subgroup of that parabolic contains H. So this question is asking, is there a best one in the same sense as we have in Theorem 3? And just to give you an idea of what the problem is here, this is a bit delicate, it's a bit tricky, because H might be G completely reducible. Remember, you can be G completely reducible, but not G completely reducible over K. And if H is G completely reducible, then it's certainly contained in some Levy subgroup of P opt, just by definition of G completely reducible. And you have to somehow set things up so that it's not contained in any Levy subgroup that's defined over K. That's the problem. So this is delicate because if H is GCR, is G completely reducible, then some Levy subgroup P opt must contain H. And so I'll just finish by, this is what I said before, by pointing out that if the answer is yes, then the other direction of C's question. And so let's see the proof again. I've seen it twice already, so maybe I shouldn't even bother writing it down. But there's still a couple of minutes left, so why not? The proof. Suppose H is not G completely reducible over K prime. Take our parabolic subgroup to be this optimal guy. So I mean not the original one of theorem 3, but this new one here. Okay, they might not be the same, right? In fact, they won't be. They certainly. Well, it doesn't even make sense if H is GCR because there isn't an optimal guy in the sense of theorem 3. So let P be equal to P opt. Then H contains P. And now we just look at the Galois group action again. So since the Galois group of this finite extension this time stabilizes H, stabilizes P. By optimality. And this tells us, as before, by the Galois criterion, that P is defined over K. And then to finish, H is not contained in any K prime Levy subgroup. Of P. Okay, that was part of the definition of what I meant by the optimal guy. So it's certainly not contained in any K Levy because K is a smaller field than K prime. So H is not GCR over K. All right. Applications of this, if you want to hear more about applications to the centre conjecture for spherical buildings, then you'll have to come along to Mike's talk on Tuesday. So thanks very much for your attention.
Questions? So you mentioned examples in G2 and characteristic 2. What
Yes.
other examples do you have?
That's the only one we have.
Go on.
So at the beginning, you gave a representation theoretic criterion for the case of SON or GLN. Is there no representation theoretic criterion sort of in the abstract in general? I mean, like there's some canonical representation that we test for.
So you can do things like, so if you're working with classical groups, for instance, then you have the natural module that they act on.
And that works.
And
that
so you can say, suppose you have a subgroup of SON. Is it true that that subgroup is SON completely reducible, if and only if it acts semi-simply on the natural module? You can ask that question, but the answer turns out to be no. Yeah. So it's yes in good characteristic, but it's no in characteristic 2 in that case, for instance. So yes, we did. It's a very natural question. We did think about it, but there doesn't seem to be an obvious way to do it. You could also ask about the Lie algebra, right? So you could ask, is it true that H is G completely reducible if and only if it acts semi-simply on the Lie algebra? And again, the answer is no. There are examples where you have a completely reducible subgroup that doesn't act completely reducibly on Lie algebra. Actually, that's very easy. Just take SL2 as a subgroup of SL2, right? Any G is completely reducible in itself, trivially, but SL2 in characteristic 2 doesn't act completely reducibly on its own Lie algebra. Whether it's true in the opposite direction, that's an open question that we've been thinking about for a while. It seems to be quite tricky.
But that also occurs only in bad characteristic?
Yeah, this sort of thing only happens in bad characteristic, that's right.
So at the beginning you said this thing about, so in characteristic 0, GCR is the same as reductive.
Yeah, that's right.
So I guess in general that's still true in one direction?
Yeah, I should have said this. I wrote down an extreme case. Any GCR subgroup is reductive. So I pointed out that a unipotent group is not GCR. If you modify the Borel-Tietz construction, then you see that if you have a non-reductive group, you can put it in a parabolic subgroup that contains the unipotent radical of that H. And so that shows you that it's not G completely
So
reducible.
is there an easy example of the failure of that in the other direction in positive characteristic?
Just take a reductive group and a representation that's, in the usual sense, that's not completely reducible. And you know there always is one in characteristic P. Yeah. And so that tells you that that's then putting your reductive group inside some GLN, and it's not a GLN completely reducible subgroup.
Okay. Other questions? So let's thank the speaker again and